Yay.
Nothing.
He's drinking it.
You wish.
All right, here we go. Periodic table arranged in order from lowest atomic number to the highest. Remember, we have our S block, our D block, our P block, and our F block. We have that marked out. Remember, our helium actually is right over here when we're talking in terms of electron configuration. Elements that have the same electron configuration tend to have the same chemical properties. So those elements that end in N, and N is whatever the period is, S1, are going to have similar properties, minus the hydrogen. Hydrogen's a little weird, but everything else in there is going to have pretty similar properties. Remember, guys, in this column, they tend to be very reactive. We put them in water. We had a little sample. Some people put a big chunk in water, but Lippy knows better, and somebody was warned about that, but he didn't know. No, it was his teacher.
Oh, that's his Dutch student.
Oh, you had Goldie?
Okay.
Oh, is that what it caught on fire?
He was probably just like, I wonder what will happen if I do this.
All right. This column is reactive. It's not as reactive, though, as this column. We're in our D block here, and then we start talking about this. Remember, this row or this column is not reactive. Why? Why, though?
They don't need any electrons.
Right, their electron shell is filled, so they don't need extra electrons, okay? This one is very reactive, fluorine being the most, because it needs one electron, so it typically will take an electron from the metal side and grab a hold of that. Remember, I'm going to personify a lot today, okay? Do not personify in your answers, okay? Personify in your mind to formulate those answers, but don't do that in your answer. This is oxygen's column. This then is nitrogen's column, and so forth and so on. But they all end in P1, P2, P3, P4, P5, P6. Okay? And we'll be able to explain the periodic trends based on protons and electrons. All right. Here's some orbital diagrams. So you guys can look at those in your notes if you wish, if you still need some confirmation on that. When we look at periodic trends, we'll come back to this slide a couple of times because we're going to talk about, for example, why oxygen is easier to, how some of the trends change based on doubling up that electron right there. And also, you know, doubling up this electron. So we're going to come back to this chart with these orbital diagrams on them. All right. Stating a trend is not explaining the trend. This is a huge thing when it comes to them grading your AP exams and me grading your AP exams. Just restating the trend, well, it increases as it goes across the periodic table. Yay, congratulations, I'm glad you know that, but that's not going to get you any points. You need to explain why that trend increases as it goes across the periodic table in terms of electrons and protons and forces and Coulombic attractions, which you spent your homework on last night, okay? Don't use that in terms of, like, you know, using, oh, well, we're located here on the periodic table, so that's why. You need to go beyond that, okay? Why is that the case? All right, it comes down to this Coulombic attraction. The Coulombic attraction, then, as you learned in your homework last night, deals with two different properties. It deals with the charges that we're working with. So, for example, as we go across the periodic table in the same row, we're increasing the number of positive charges that are pulling on those electrons, okay? So that's the top part of Coulomb's law. The bottom part then deals with distance. As you increase the distance, that force decreases. So those are the two parts of it. You don't have to do any mathematical computations using Coulomb's law. There's no math with this. Now, if you take physics, if you take upper level chemistry later on, you might have that. But in this course, you need to understand how to apply the law, but not calculate it. Okay? All right. Key words, key concepts, things that they just start salivating over when they read your exams in Salt Lake City.
They read it in Utah.
That's where they have in the past. I would assume that it's the same this year. I haven't heard. Columbic attraction, this electrostatic interaction between the positive nucleus and the negative electrons. As you increase the charge, you're going to increase the force. Increase the distance, decreases the force. And then something called effective nuclear charge, which I spoke about just very briefly a couple minutes ago when we were talking about your homework. Yeah, I said effective nuclear charge. Didn't I? Didn't I say?
Saying you pounded it in your
Yeah, pound it in your heads and honors. Yes. Apparently I didn't pound it into everyone's head. We didn't spend a lot of it in regular chem, but in honors, I like, boom, boom, boom. Effective nuclear charge is the net positive charge experienced by the valence electrons. You can figure it out by taking the equation Z minus S, where Z is the atomic number, and S is the number of electrons in the orbitals that are closer to the nucleus. In other words, the non-valence electrons. And that'll tell you your effective nuclear charge. The energy required to remove the outermost electrons from a gas from a neutral atom in its ground state is called the first ionization energy. Why is it called ionization energy? Because you're creating an ion. Okay. Remember what an ion is. An ion is an element or an atom that has a different number of, oh, that's not good. That's not what I meant. I don't know. Protons and what are not equal? Electrons. Different number of protons and electrons. If you have more protons than electrons, that is called a cation. And it has a positive charge. If it is the opposite, if you have more electrons than protons, it's an anion. And that is a negative charge on that guy. Okay, remember those terms, I hope? Or you're learning them?
Yeah.
I could not take one cabinet and just jump it.
He's the second child that I've ever done it with, so we'll see. I'm very proud of him so far. He got a 3 on the exam. He was from China. And that was the year that the pandemic hit. And so they didn't test on all the units. So it's kind of hard to know how it would have worked out. But so far, so good. Yeah. All right. So first ionization energy, then, we are pulling an electron away. Okay. And you'll oftentimes see, or you'll see the trend. I'm trying to see if I have a chart here that shows that. Yeah, we're getting to it. Okay. So first ionization energy, I don't know if you have, is this in your packet? Okay. Yes. First ionization energy then increases as you move across the periodic table. So it's going to get harder to remove the electrons in fluorine versus lithium. Why?
They're more stable.
Why?
Because they have more rounds.
No.
What's the question? They have more protons.
Protons. It has a greater effective nuclear charge. okay? As you move across the periodic table, you're adding in more protons, okay? So when I give you an analogy here for this, this is how I talk about it, okay? When you are in over here, you have one parent watching over you. It's pretty easy to get away with stuff.
So true.
Here, you have two parents watching over you. A little bit harder. Now you have a parent and a maternal grandmother.
Now you have a game.
Two grandparents and two parents. Here you have 5 people watching over you, 6 people watching over you, 7, 8. By the time you get over here, it's almost impossible to get away with anything. Okay? So, as you move across, you're adding more effective nuclear charge in. You're adding more protons pulling on that outer electron, preventing it from getting pulled off.
So protons to pick the nuclear charge.
Yep. Okay. Now, as we move down, you're going to decrease ionization energy. Okay. So this is my analogy where here we've got our little baby. You're holding it really close. Okay. Here you've got the toddler. They're right by your side. They're not going anywhere. Okay. You're using that pinky. You're controlling them. They're not going anywhere. Here, they're in kindergarten, elementary school,
Okay.
middle school, high school, college. By the time they get to college, good Lord, there's all kinds of stuff that you get away with. Okay? So it's easy to get away with stuff. And you've only got one parent watching over you. So francium gets away with all kinds of stuff. Okay? Yeah. It's really easy to pull that electron off.
I love
Okay? Yeah.
I got a question.
Yeah.
So, which direction is greater ionization energy? So, like,
As you go across, it gets greater. As you go up, it gets greater.
yeah, but like, let's say, you have lithium,
Okay?
right?
Lithium.
So which one would have so which one would have more ionization energy, sodium or beryllium? Or I mean, helium or beryllium? Like, because
Helium would.
You like use both of them. You just kind of like go like this.
Yeah.
Like
Typically, they're going to be asking you a question that is comparing either vertically in the same column or horizontally. Okay? Probably not. But in that case, helium's going to win. Helium's going to have it's going to be helium is the hardest one to pull an electron off of.
I know, that doesn't fit.
Why? Because it has the least distance and it has 2 protons pulling on that.
I like neon.
Okay? So distance is a big, big factor. Okay?
Sorry, I was stretching.
And that's why if you look back at Coulomb's law, I don't know if I actually have the actual formula for it in here. I know we've got it. I think we had it in the homework.
You have like phosphorus and oxygen.
No, Ben. I was right.
Benjamin, you might have.
Well, he was over here he was over here with a handful of just sniffing it.
Okay, yeah, here we go. So if you look at actually Coulomb's law here with the force, okay, your charge is up top here, your distance is actually squared. So that means that that's factoring in more than just the charge. Okay, so that distance is going to make more of a difference.
So that we wouldn't need to know for the
For
AP
each of the
exam,
following pairs.
because that's like the mathematical.
Yep.
Okay.
Yep. But it's good to have a good conceptual understanding of it. Okay. Did that answer your question?
Yeah.
Okay. All right. So first ionization energy, we're pulling that electron away. When we look at the trend of this, it goes up. Helium's the highest, and then it drops down here to lithium. It goes to beryllium, but then it drops down to boron again. Okay, do you see how it drops just a little bit there? let's talk about why that dip happens. I'm going to go back to here and talk about it. Okay? Here, this one is the closest and it's got 2 positive charges. We take a little bit of distance here, okay? And then beryllium's higher because it's got 2 electrons in it. Remember, it dropped down just a little bit when we got to boron. Why?
Is it because it's a little like shallow?
Yeah, it's a distance. The distance is increased, okay? Because remember, you've got your 1s, you've got your 2s, your 2, so 1s, 2s, 2p's just a little bit outside the 2s. So the distance is increased just a very little bit, and that's why that dips down there, okay? Then we increase, why? Why are we increasing here? What's causing the effective nuclear charge has increased. We've increased the number of protons. But then we dip down. Not this time. Nope.
I'm getting
What has happened here? Here, they're separated. Here, what has happened? It's doubled up. There's 2 electrons in that shell. Like charges do what? Repel. Like charges repel. You've got 2 electrons in that orbital right now. So it's like, get out of here. I don't want you here. Go. Okay?
That's awkward. I'm getting it over here.
These are exhausting.
Good job, Ben. Well, now it's all the way over there.
So here, it dips down a little bit because of that repulsion. Because the negative, those 2 have doubled up, and it's like repel, like charges repel. But then it increases because we're increasing the effective nuclear charge. Okay? Then we dip down again. What's happened here? It got further away. We've added another electron shell. We're in the 3rd electron level now. So the distance is increased. Increase in distance decreases the force of attraction. So it's easier to pull that electron off. The kid's gone to kindergarten. Okay, we're able to pull him away from mom.
No, that's when one parent's watching.
All right. Second ionization energy is pulling another electron off of the same atom. It gets harder to pull the second electron off. Why?
They repel.
So true.
We have the same number of protons pulling on fewer electrons. Okay? So you've got more protons there pulling on fewer electrons. When you're trying to pull the second electron off. So you've pulled one off, now you're trying to pull another one off. It's harder to pull off because your effective nuclear charge is higher. You've got more protons versus electrons. That makes sense? Now, when you see a very large jump in these ionization energies, that means that you've pulled all of the valence electrons off and you're back to a noble gas configuration. So that's what you're looking for. Now, how does that look numerically? So here, we have a very large jump where? There's a couple places. Okay, between here and here, and between 2nd and 3rd. Okay, so that means that between 2nd and 3rd, when we lose 2 electrons, we're at a noble gas configuration. So that means that we have an S2 for our valence electrons. We have 2 valence electrons. It means that that is going to be one of the elements in that second column. Because when you pull 2 electrons away, you're back to the other side.
That's where the big gaps are.
Where the big gap is. Yep. Okay. And then here, we go 1, 2, 3, 4, 5, 6, 7, 8. We do it again. Okay, so you look for the big gap. Where that big gap is, where that big jump is, that means that this guy, whatever he is going to be a noble gas. How many electrons did we have to pull away to get there? 2. That means that you would have been in that second column.
So that would mean that the second and 10th were the same column. Like number on.
Mm-hmm. Well, no, the second would be the first column. This would have been in the second column. So they're asking you, like if we had, but we're trying to identify what the thing is. So this is magnesium here. All right, are we good on ionization energies? Everybody okay? All right. The next one that you have to wrap your head around is atomic radius. Okay, and I've got a little bit of a diagram here. And let's talk about why we increase as we go down. Okay, this is my analogy of getting out of the shower, putting on your underwear, putting on your first summer clothes. Now we're into winter, so we're putting on a sweater, we're putting on a sweatshirt, and now we're putting on our parka. Okay, you're adding layers, you're adding levels as you move down the periodic table. It's the Russian dolls. I used to go and get the Russian dolls from Mrs. Nichols. She's gone now. I know. Okay, but we're adding layers. So of course it's going to get bigger as you add layers. Does that make sense? It's pretty intuitive going down, I think. It's the going across that you're like, we're adding more protons and electrons. Why would it get smaller? Because you're adding more protons. Okay? They're pulling it in tighter and tighter and tighter as you go across. Okay? That effective nuclear charge, that charge is getting bigger, so it's reducing that distance. It's pulling it in. So as you go across, it's going to get smaller. As you go down, it gets bigger. And again, I think the down is easy to kind of visualize. It's the going across that you've got to really kind of tweak your brain around. Okay. Atomic radii, we talked about that, how that's increasing. I think that's pretty easy to kind of grasp. All right, now this guy is fun. You ready?
Yes.
All right. Now, remember what ions are. Are you going to write on here for me? Yes. Okay. Ions are a different number of protons and electrons. They do not equal each other. Okay. Your anions, then, if we talk about, oh, wait a minute, did they talk about cations first? They talk about cations first. Okay, so we'll talk about cations first. Cations are where you have more positives than you have negatives. So because of that, your protons are able to pull that in. The thing's going to get smaller as you move across. So your first one might look like this. Your next one, if you've pulled 2 electrons off, it's going to get even tighter because you've added an extra electron or proton in, and now you've pulled off 2 electrons. So for calcium, for example, you've pulled off 2 electrons. 2 electrons are gone, and you've got 2 more positives versus the negatives that are there. So for calcium, that would be, what is it, 20? 20. You've got 20 protons pulling on 18 electrons because you pulled off 2 electrons, making it a cation. So that's going to pull in tighter than potassium with 19 protons versus 18 electrons. Good? This is going across. Your cations are going to get smaller as you move across because you're increasing the effective nuclear charge on them versus the number of electrons that are there. So a cation, an ion of calcium, is going to be smaller than an ion of potassium. Now, anions are larger than their parent atom. So if you compare, for example, fluorine minus versus a fluorine without an electron taken away, here you've got here you have 9 electrons and 9 protons. Okay. For this guy, you've got 9 protons and you've added an extra electron in. It's a negative charge. So you've added an extra electron in. It's grabbed an electron from somewhere else. So now you've got 10 electrons. So you've got 9 protons pulling on 10 electrons. It's going to be bigger than its original fluorine, because there's fewer protons than electrons there. Okay. If you look at oxygen, then it's going to have 8 protons. How many electrons would it have grabbed? No. Oxygen's going to grab how many? It's going to get 10. Yep, it's going to have 10 electrons. Okay? Because it's going to be a 2 minus charge, yes? Everybody buy that?
I agree.
Okay? So if that has 10, so this, if we're comparing oxygen anion to a fluorine anion, which one's going to be bigger? Oxygen. Oxygen's going to be bigger because it's got 8 protons pulling on those 10 electrons. And there's a diagram with actual numbers to substantiate my claims, to give you an idea. Electron affinity, then, is the amount of energy involved when an electron is accepted to form a negative ion. Those values tend to be negative to show the energy is released. In general, it increases left to right. Okay, so there's your electron affinity. These guys tend to want electrons more. Again, it's not going to really apply. It's not really going to apply to your noble gases. It's more truncated right here at fluorine, but the idea is the same. We have a trend of decreasing electron affinity when moving down because you're moving further away. The distance increases from that electron. All right, so there is a trend for that if you'd like to look at those. And again, you get a little bit of a jump here and then dips, and because your noble gases really don't need electrons. Okay, and then we talk about electronegativity. So the electronegativity is attracting those electrons. What is the most electronegative element on your periodic table? Fluorine.
Yeah, because helium.
Helium's already fine. It doesn't need any more electrons. So it's fluorine. Okay.
RT.
We had, I even gave you table with this back in the day where I said that this guy had a 4, this was a 3.5, this was a 3, 2.5, a 2, hydrogen is 2.1, this guy ends up being like a 0.7, okay? They actually gave value, I think it was Linus Pauling that did that. They actually gave values to these. And it's those differences in electronegativity values that determine whether it's an ionic bond or a covalent bond. We'll get into that in our next unit. But that increasing electronegativity, how badly it wants an electron. Remember, everything's aspiring to be a noble gas. It's either going to gain electrons to do it, it's going to share electrons, or it's going to give electrons away. All right, here's your electronegativity differences. Again, that's what's going to determine what kind of bond you have. And we're going to get more into these covalent, polar covalent, all of that fun stuff in our next unit. If you have no difference in electronegativity, it's nonpolar covalent. The electrons are shared equally. Here, hydrogen and bromine, you're going to have polar covalent. There's a difference in those values. So bromine is down here. It's probably, I'm guessing it's around 3-ish. I'd have to look it up. Hydrogen is 2.1, so that ends up being a 0.9 difference in electronegativity. Oops, I went the wrong direction. And then large differences in that. So for example, sodium, that's probably around like 0.8, and chlorine, that's probably like a 3.5. That's going to be a very large difference. That's going to give you an ionic bond. Essentially, the electron would have gotten transferred from this sodium. It's going to give that electron away to the chlorine. It's not going to be just sharing it. Gives it away. All right, so between these, you've got lithium and sodium. I'm sorry, sodium and lithium and fluorine and oxygen. Between those, which one, so lithium versus sodium, which one's going to have the highest first ionization energy? Li, right. Why?
No, you cannot say that.
Because lithium has less distance, right? It's closer, the outer electron is closer to the nucleus, okay? Always go back and think about Coulomb's law. What part of Coulomb's law is being affected by this? Well, here it's going to be the distance. So it has a reduced distance to the nucleus, and that increases its first ionization energy. All right, what about fluorine and oxygen? Which one is going to have it? Fluorine, because it has a higher effective nuclear charge. Okay, larger atomic radius. Which one's going to be bigger? Sodium. Okay, it has more energy levels. Yep. Fluorine and oxygen. Which one's bigger? Oxygen, because because fluorine has a higher effective nuclear charge.
Okay.
Higher electronegativity.
Lithium.
Lithium. Okay. Lithium has a reduced distance to that electron, so it's going to hold on to it tighter. Fluorine and oxygen. Shouldn't even have to think about this one because you should know automatically fluorine is the biggest, but that's not an answer that you can give on a test. That is not an answer you can give on a test. Fluorine has a higher effective nuclear charge. Okay. Yep, this is the last one. Okay, so rank the following from smallest to largest for atomic or ionic radius. So we're looking at these three. You've got 2 ions and an atom. Which one's going to be the smallest? You list that first. Which one's going to be the biggest?
It's same order.
Yes, indeed. No. Yeah, it is. Yep, you're right. Same order. This is the answer. Okay. Carbon, nitrogen, oxygen. Reverse order. Yep, you're going to reverse these two, and you'll have the answer. Chlorine, argon, potassium.
Chlorine.
Yes.
Chlorine is going to be smaller, and then argon, and then potassium. So it's already in the right order.
Wouldn't argon be then chlorine? Because it has no proton.
Oh, wait. Yeah, you're right. Argon is going to be the smallest, chlorine, and then potassium. Lippy was wrong. Imagine that. I know. Get used to it.
We get to part two.
All right, so this one's in the right order.
I am sure.
7-1 is homework. You have a quiz on Monday. 1-7. 1-7. I got dyslexic there. Sorry.
No.
What is the quiz gonna like? What's it gonna look like?
How big is it?
Probably a front and back page. It would. I have to write it. It'll be done by Monday. No. Oh no. Because you're in a